Yesterday we were looking at molecular formulas or ionic formulae, and we were trying to find the percentage composition of each element in it. And today we're going to look at the opposite. We're going to be told the percentage composition, which can be found by different analytical techniques, and we're going to try and work out what the formula of something is. It won't tell us the structure of it, okay? It'll only tell us the formula. You need a lot more, you need things like infrared spectroscopy and stuff like that to actually work out the structure of something. You need a lot of information. But knowing the percentage composition, so how much hydrogen, how much carbon, or whatever, is actually something that we can use to find at least its molecular formula, so to find how many of each atom would be present. If we know the molar mass, that tells us if we're correct or not with that as well. Okay, so in this one here, we're going to have some chemical made up of carbon, hydrogen, and oxygen, because they pretty much add up to 100%. It adds up to 99.7, which is close enough to know that we don't have much else in there, or nothing else in there, or that it's correct with the rounding off. So, how to approach it? Well, just like when we were looking at other things as a balanced equation, we're going to do the same sort of thing here. However, we know it's got carbon, we know it's got hydrogen, and we know it's got oxygen. We know those together will make our mystery chemical. Okay? We don't know the numbers in front of these yet, that's what we're going to find. And we don't know the ratio over there, that's what we're going to find. So what I'm going to do is I'm going to go the same process as I did before. I'm going to turn it into a table. So hopefully starting to see a bit of a pattern forming here. And just like before, what do we think will go as the headings for my 3 rows? Brilliant. So N, M, and MR. Or capital M. Okay? MR in this case is atomic mass because they're atoms. Okay? We're not worried about the fact that they would be found as elements. That's not actually something we need to worry about. So I can just get those numbers directly off the periodic table. So I've got 12.0, 1.01, and 16.0 there. I don't know my mass. I only know percentages. But what did we do yesterday? What was the assumption we made to turn our masses into percentages?
100 grams.
Cool. We presumed that we had 100 grams of our product. So we're going to do the same. Because we're given percents. So let's say, okay, well, let's pretend that they're their mass then. Alright? Because that would be right. If we had 100 grams, then 40 grams of it, 40% of it is carbon. So we put in 40 grams there. Seems a bit crazy, but we've only got 6.7 grams of hydrogen. And 53 grams of oxygen. Okay. Now we can actually work out the amount of each of them. So we'll have a go at that. 40 divided by 12, and I'll need my calculator out to do this one. Sorry. I should do it the right way. 3.3 recurring, so I'll just put 3.3 because these values are only, oops, it shouldn't be 0.0. These values are only 2 significant figures, so these ones should be as well. So 3.3, 6.7 divided by 1, I think I can work that one out, 6.7. And 53 divided by 16 gives me 3.3125, so 3.3 as well. Now to find our mole ratios before, what were we dividing by to make one of these 1? Itself. Which one are we going to choose? Which number do we choose? Okay, so if we divide both by 6.7, that one would be a 1, but that would make these fractions. We need to have, well, the rule is you divide by the smallest number in this row. So what's the smallest number in this row? 3.3. So to make our ratio, we're going to divide everything by 3.3. Okay. If I have a look there, 3.3, well, that's going to be a 1. That's going to be just over 2, but we can only work with whole numbers here. So it is going to be a 2, and that's going to be a 1. So that tells me that there's 1 carbon, 2 hydrogens, and 1 oxygen. So if I put all those together, how would I write that as a molecular formula?
CH2O.
Perfect. CH2O. Alright? And if so that makes 1 mole of them. Perfect. Alright, now my problem here is, if I work out my molar mass of this, what does it add up to? 12 plus 1 is 13, plus another one, which is 2 hydrogens, is 14, plus 16. What's 14 plus 16? 30. But it said to me the molar mass was 60. So what do I have to do to my entire equation to make it add up to 60, not add up to 30? Fantastic. So what we have here, and I'm going to draw on this because I'll photograph it in a moment. What we have here is a thing called the empirical formula. The empirical formula is the simplest ratio of the elements. All ionic formulae are actually empirical. All ionic formulae are actually empirical. They're the simplest ratio of ions. This is an empirical formula. So I'll say that again. The simplest ratio of elements in this stuff here, in this unknown compound. We basically look at what the molar mass is compared to the molar mass of the empirical formula and look at a ratio there. This one only adds up to 30. You guys have got it brilliantly there. To get its molecular formula, we have to multiply it by 2. So this one's 30 grams per mole. We need it to be 60 grams per mole, which is timesing it by 2. Now, this is still a formula. It's not 2 moles of that. So how would I write this as a formula? Okay, so I could go 2 CH2Os, but that would tell me I've got 2 moles of CH2O. That's not what I need. I need it to be 2 carbons, 4 hydrogens, 2 oxygens. I could use brackets. That would still tell me that they're bound together as 1 carbon with 2 hydrogens, 1 oxygen.
C4.
C2. H4. O2. Okay. Okay, so I'll answer that again. If I put a 2 at the front, it means I've got 2 of that molecule. So I haven't changed the molar mass, it'd still be 30. The big number has no effect on molar mass. Only the little numbers have effects on molar mass. Okay, so when I'm calculating molar mass, I disregard any numbers in front. I only look at what atoms are inside it. So I need it to have 2 carbons inside it, 4 hydrogens inside it, and 2 oxygens inside it. Okay? So that will be our final answer. So let's just go through that process again really quickly. First of all, we laid out the elements that are involved across the top like a table. We put N, M, M down the side here, and we turned the percentages into grams, assuming that they will add up to 100 grams. So we've made an assumption. Let's assume we have 100 grams of our stuff that has been analysed. So the percentages become masses instead. Because once I know the mass and the atomic masses of everything, I can find how many moles I've got in 100 grams. Once I know how many moles I've got, I divide by the smallest number, and they should come out as very close to whole numbers. That will give me my empirical formula. Once I know the molar mass of my empirical formula and I compare it to what the molar mass should be, I know whether that's the right answer or not. If it's not, it's because this is twice as big as this, or this is 3 times as big as this, or whatever, and I multiply each atom by that multiplication factor. Okay. Now, a little word for you. If you get a number like 2.5, then it means that you know that it's wrong. Okay, so if it was 1 to 2.5 to 1, you know that it should be 2 to 5 to 2. You've got to find the simplest whole number ratio. If it was, let's say, 1 to 1.33 to 1, what do you think it would be then?
1, 9.
Sorry?
It would be 1, 1, 9.
So no, 1.33 is 4/3. So it would be 3 to 4 to 3. So you need to know your fractions pretty well, your thirds and your halves and your quarters. Okay? So that little bit of maths is really important. And sorry, I'm just going to put in one more note there before I stop the video, that this is what it was after, our molecular formula. Alright. Any other questions before I stop the video? Awesome.